Okay, welcome everyone to this session, the parallel session on general relativity and cosmology. I believe this is the first session on this topic. And we have one invited talks and a few contributed talks after that. So there are a few things which I wanted to announce before we get along. So first thing is we will take the questions only at the end of the talk. So people who have joined via Zoom, you can either raise your hand and I will try to take the questions as they come. You can also post your question in the chat box here on Zoom. And also there is a Slack channel. Now the link to the Slack channel is given in the chat box here. So you can always have discussions there in case we are unable to take all the questions because of time constraints. Also we are going to record this session fully, so I hope the speakers are fine with that. And I also request the participants not to try to record this, otherwise it interferes with the default recording. So I think we are now we can now start the proceedings. So our first talk is an invited talk by Sriramkumar, and he will be telling us about signatures of enhanced scalar power on small scales. So Sriram, please go ahead.
Thank you, Tirth. I should begin by thanking the organizers for inviting me to give this talk. As is well known, on large scale, the primordial scalar power spectrum is well constrained by the CMB data. However, there is relatively less constraints on smaller scales, scales larger than, say, in terms of wave numbers, about 10⁴ megaparsec inverse or so. And therefore, there has been a considerable interest in the recent past to understand what are the observational signatures if there are enhanced power on such small scales. Why do we require, what is the motivation for considering such enhanced power on small scales? As we shall see, there will be greater levels of primordial black hole formation if you have such larger power on small scale when compared to the CMB scales. And these will also induce so-called secondary gravitational waves, which may be of amplitudes which are possibly which can be detectable, which are detectable in the very near future. Here is a plan of my talk. I will first talk about constraints from the Planck data on the CMB scales. Then I will discuss as to how to enhance power on small scales. To some extent, we understand how to enhance power even when we have examined certain models which lead to features in the primordial power spectrum over the CMB scales. And then I will discuss the implications of such enhanced power to primordial gravitational, to the formation of primordial black holes and to the formation of secondary gravitational waves. What happens is that when you try to enhance power, you need to deviate from the simplest paradigm of slow roll inflation. And it has been well understood that when you deviate from slow roll inflation, the non-Gaussianities, larger levels of non-Gaussianities, larger when compared to what slow roll inflation produce, are generated. And therefore, one has to, if you are trying to enhance power on small scales, you also need to go on to understand what are the effects of non-Gaussianities, both on primordial black hole formation and the secondary gravitational waves and the strength of secondary gravitational waves. And there is another mechanism for generate features in the primordial spectrum. This is also well understood. And this is due to what are known as squeezed initial states. You can choose squeezed initial state so that they lead to specific features in the power spectrum. We will, something that is interesting is that these squeezed initial states lead to larger levels of non-Gaussianities compared to what you see, from deviations from slow roll inflation, particularly in the so-called squeeze limit. And it is interesting to understand whether these can have non-trivial implications. And then I will close with a summary. Let me point out that this talk is based on these two preprints, work done with my graduate student Raghavendra and my postdoc Pankaj Saha and Professor Joseph Silk. What are the constraints on inflation from Planck? Well, you know how perturbations are generated during inflation, or rather why you require, I'm sorry about this, why you require epoch of inflation. You require an epoch of inflation to overcome the horizon problem. What has been plotted in this graph or in this figure are two quantities. In blue, you have the wavelength of the perturbations, which are always proportional to the scale factor. And in red is the Hubble radius. And I have indicated the red the Hubble radius during the behavior of the Hubble radius during the radiation dominated epoch. The x-axis is the number of epochs, logarithm of the scale factor. And on the y-axis are the logarithm of the Hubble radius and the wavelength of the perturbation that have been plotted. And if you have only a radiation dominated epoch, these modes will be outside the Hubble radius at early times. And this is the horizon problem associated with the hot Big Bang model. But if you have an epoch of inflation, you can ensure that the modes are inside the Hubble radius and overcome the horizon problem. How do you achieve inflation? Well, as is well known, you achieve with the help of scalar fields. And there are a wide variety of inflationary potential to choose from. You have large field models where the scalar field rolls down to lead to inflation for values of the field which are large compared to the Planck mass, or you can have situation where phi is much smaller than MPL and generate inflation, or you can have more complicated scenarios. Now, what typically happens is that the modes over which the CMB scales emerge from occur in this large field model during the early stages as the field rolls down the potential. The hope is that if there is enhanced power on small scales, which lead to larger levels of secondary gravitational waves and primordial black holes that can possibly be detected, well, one hopes that you can constrain the inflationary potential over this domain as well before inflation ends at the bottom of the potential and leading to reheating. And what are the constraints on the CMB scales? Well, this is the Planck CMB data. What has been plotted are two quantities. In red is the best fit primordial power spectrum, which has been assumed to be nearly scale invariant, characterized by a certain amplitude, which we know very well. It's called the Kobe amplitude and Kobe normalization or Kobe amplitude. And NS, as we shall see, is very close to 0.96. Remember, the scalar power spectrum is written as k power ns minus 1. So you are essentially talking about a power spectrum which is slightly red tilted, which behaves like k power minus 0.04. And this red curve corresponds to the angular power spectrum generated from a scale invariant, nearly scale invariant primordial power spectrum. And it fits the CMB data very well. And the blue curves are, the blue dots with error bars are the CMB data. And even I was mentioning as to how there can be deviations from slow roll even over CMB scales. And these deviations can lead to an improved fit to the CMB data. I will come to that in the next slide. Before that, let me talk about the constraints on the tensor to scalar ratio and the scalar spectral index. The tensor to scalar ratio is the amplitude of the primordial tensor perturbations, which has to be less than about 0.05 or 0.06. And the scalar spectral index is very close to 0.96, as I was just mentioning in my previous slide. And as is well known by now, the Starobinsky model, the original R plus R squared inflationary model, fits that data very well, as it leads to tensor to scalar ratio, which is 0.003 or so. So I was talking about features in the primordial spectrum. Notice this corresponds to this nearly scale invariant amplitude is the Kobe amplitude. I'm talking about the CMB scales of about 10 power minus 5 to about 1 megaparsec inverse. And this power spectrum fits is what I had shown earlier. Well, if you have a feature, focus on this feature, for instance. If I have a sharp drop in power on large scales and Kobe normalized amplitude on relatively smaller scales, then it is known to improve the fit to the CMB data. And we have explored such models. Therefore, we know how to enhance power on smaller scales compared to larger scales. Now, all we need to do if you want to generate larger power on even smaller scales, well, you need to shift this amplitude to the Kobe normalized amplitude. And evidently, you have to enhance power like this on even smaller scales. And this can be achieved through a certain class of models, which we will refer to as ultra slow roll unpunctuated inflation. So what is our goal? To enhance power on small scales. If you want any features in the primordial spectrum, you need to deviate from slow roll inflation. And what I have displayed here are a certain class of models which are referred to as ultra slow roll inflationary models. What do these models do? Well, what I have plotted here are the first 3 slow roll parameters. If you have pure slow roll inflation, like the popular m squared phi squared model, what would have happened is that epsilon1 would have been at the order of 10 power minus 2 or so, and it will remain there until the end of inflation. Epsilon2 will also be roughly of the same order, and epsilon3 will be completely negligible. What happens in these potentials is that they contain a point of inflection. In this phase portrait drawn here, this is phi d phi by dn, which is like the velocity of the field. Remember, n is the number, denotes the e-folds, and this vertical line is the point of inflection. What happens is that as the field approaches the point of inflection, the first derivative and the second derivative of the potential vanishes. Therefore, the field's velocity drastically comes down, as you can evidently see here. Notice this is the inflationary attractor. Various trajectories join the attractor, but as it approaches the point of inflation, as the field approaches the point of inflection, the velocity of the field drastically comes down, and this is reflected in a sharp drop here of the first slow roll parameter, where the first slow roll parameter drops exponentially, and this leads to relatively larger values of the second slow roll parameter and the third slow roll parameter, and these deviation from slow roll inflation are what leads to features, or equivalently the sharp drop in epsilon1 leads to a rise in the scalar power spectrum on smaller scales. And there are another class of potentials which we have considered. These are the so-called punctuated inflationary models. Again, they contain a point of inflection. The field slows down here, and there is a domain where epsilon1 drops drastically, and it is what leads to enhanced power. But in these models, in contrast to what I had shown in the previous slide, there is a brief epoch, extremely brief epoch, lasting for less than an e-fold, where inflation is actually interrupted and it is restored immediately after. And for that reason, these are called punctuated inflationary models. We have also examined another class of scenarios which we refer to as the reconstructed scenarios. It is often, complicated, to construct these inflationary models. There are many models in the literature now, but it is nevertheless challenging to construct these inflationary models that lead to the desired behavior and therefore to enhance power on larger scale, on smaller scales. In contrast, if you work with a particular form of epsilon1 of n, a particular form of the slow roll parameter, what we have done is that we have taken one ultra slow roll inflationary model, one punctuated inflationary model displayed in red, and we have tried to construct an epsilon1 which mimics them, and we will see that they also lead to enhanced power. The attractive nature of these reconstructed scenarios is that they are easy to construct, in contrast to the potentials which are often difficult. Now, the only challenge, there is a caveat here, we can construct the potentials from these epsilon1 of n numerically, but it is challenging to construct the potentials analytically, and this is something we are working on. So what is the effects on the power spectra? Well, it is clear, it is very similar to the power spectra that I had displayed earlier in the context of CMB physics. What we have is a nearly scale invariant spectra on one side here. Okay, nearly scale invariant power spectra. The challenge with these inflationary models, you have to tune the parameters such that ns is 0.96 and r is smaller than 0.05. And here in red, we have plotted the scalar power spectra, and in blue, the tensor power spectrum. Notice the tensor power spectra is hardly, has any feature other than the drop in power on small scales. In contrast, the scalar power spectra exhibits a sharp rise and leading to as large an amplitude of about 10 power minus 2 or so at a scale of roughly 10 power 14 megaparsec inverse. And if you want the increase in power, and the location of the peak in power depends on the inflationary potential. You need to choose potentials and you need to tweak your parameters so that you have the desired amplitude and the desired location in the peak. And there are many inflationary models today which will allow you to construct them. And these are the power spectra and the reconstructed scenarios. What these reconstructed scenarios allow us to do easily is to change the location of these peaks and also lead to broader peaks. So what are the observational consequences of this enhanced power on small scales? As I have been mentioning, there are two observational consequences. I'm sorry, I did something where it is. There are two observational consequences. One is leads to enhanced formation of primordial black holes, And it will also lead to secondary gravitational waves, as I shall describe over the next few slides. Well, what happens is as follows. Remember, we are interested in scales which are in wave numbers larger than about 10⁴ megaparsec inverse or so. And these scales re-enter the Hubble radius during the radiation domination epoch. And when they re-enter the Hubble radius, if they have a sufficiently large amplitude, they can collapse to form black holes. And what one is interested in, the fraction of such objects that will go on to form black holes, primordial black holes, and that is evidently depends on the distribution of the density contrast P of delta, which we shall assume to be Gaussian as illustrated here. It is described by a width sigma square, which is determined by the primordial power spectrum and the scale over which you smooth this smooth the distribution, primordial distribution, or equivalently the distribution of the density contrast. And this scale over which you smooth, which we typically smooth with a Gaussian window function, also is related to the mass scales, and that determines the mass of the primordial black holes that will form. And there are a couple of further points I need to make. Notice you need a certain critical density to be generated in order for these density perturbations to go on to form black holes. And this delta C, we will assume some typical values. And one of the things I want you to appreciate is that this fraction of primordial black holes that contribute to the cold dark matter density today is evidently strongly dependent on this beta M. And this beta M is strongly dependent on delta C. In fact, it is exponentially sensitive to delta C. Even a small change in delta C will change the extent of black holes produced considerably. So in summary, we are focusing on scales that re-enter the Hubble radius during the radiation dominated epoch. Given a primordial power spectrum, it is well understood what is the P of delta during radiation dominated epoch. This can be related through the transfer function. And given a P of delta, okay, we can calculate the beta of M, and from there the density, the fraction of primordial black holes that contribute to the cold dark matter density today. And let us go ahead and calculate what are the FPBH for the different inflationary models that we have considered. And for the specific inflationary models we have considered, these results are plotted in red here, and these blue, green, and yellow or orange curves correspond to those reconstructed scenarios. As I said, they allow us to shift the locations of these peaks and the width of the peaks fairly easily. If you look at the original inflationary models, you find that they can lead to a fraction of FPBH, which is like about 1% or so, provided you assume delta C to be fairly small. This solid curve corresponds to a delta C of about 0.3, and this dash curve, if I recall, corresponds to a delta C of over 0.35. And this dotted curve that lies very low here and is hardly visible here corresponds to a delta C of 0.5 or so. In other words, as you increase delta C, and there is a debate going on as to what should be the value of delta C that one should work with, the number of primordial black holes produced drop drastically. What are the corresponding imprints on gravitational waves? Why do these secondary gravitational waves arise? Well, at the leading order in perturbations, there is something called the decomposition theorem, which suggests that, which tells you that the scalar and the tensor perturbations, evolve independently. So if this h of k were the primordial tensor or the linear tensor perturbations, then there will be no source term unless there is some anisotropic stress or so at later times. During inflation, they will have no sources, and those are the primordial gravitational waves. Here, what we are interested are the second order gravitational waves, or rather the gravitational waves generated at the second order. At this order, the scalar and the tensor perturbations get coupled, and in fact, the scalar perturbations, the second order scalar perturbation shows the tensor perturbation. The fact that these are second order scalar perturbations is evident from the point that this source term contains products of the Bardeen potential. This Bardeen potential, remember, we are interested in modes which re-enter the Hubble radius during the radiation dominated epoch, and these Bardeen potential during the radiation dominated epoch can be related to the primordial curvature perturbation through the standard transfer function. And given this transfer function and the primordial power spectrum, we can calculate the energy density associated with the secondary gravitational waves. And this energy density of the secondary gravitational waves, which is rho GW of k eta, is often described in terms of this dimensionless quantity when it is divided by the critical density. And this can be expressed in this form. I'm not going into the details. What you are interested in modes, as I've been repeatedly saying, that re-enter the Hubble radius during the radiation dominated epoch. So if you have a source which contains products of the Bardian potential, using this source, you can calculate what is the inhomogeneous solution to the gravitational waves, and you can calculate the corresponding power spectrum or the equivalently the energy density associated with the gravitational waves. And as you can imagine, if the source term contains product of the Bardian potential, the energy density will contain 4 terms involving the Bardian potential or equivalently the primordial curvature perturbation. Since we are assuming the primordial perturbations to be Gaussian, this 4-point function can be expressed in terms of the 2-point function, and that is what has been done. So you have here in the expression for omega GW k eta, this is evaluated at 8 times during the radiation dominated epoch, very close to the epoch of decoupling. It contains products of the primordial scalar power spectrum. All you need to do is that take your primordial power spectrum that I had displayed earlier, plug this in and calculate this quantity. This, as I've been saying, is evaluated during the radiation dominated epoch. Gravitational waves in the sub-Hubble domain behave very much like radiation, using the ratio of omega GW of k eta to the omega R of radiation. You can calculate what is the omega GW today, and as I just mentioned, it is related to omega R, and of course, you know, the omega GW at the epoch of, say, decoupling. And what is the omega GW generated in these inflationary models of interest? I have 5 minutes, Steve.
Yeah.
Okay, I should be able to complete them in time. Okay, what are the omega GW generated in these models? These red curves are the omega GW that have been generated in these models. This is in the ultra-slow models. This is in the punctuated inflationary models. These curves here on top are the sensitivity curves of the various ongoing and forthcoming missions. And evidently, you can have a large enough power that, you know, can be possibly detected by these gravitational wave observatories. Just a couple of remarks. If you are interested in the primordial tensor perturbations, you know, then they will be at order of about 10 power minus 16 or so. The second order primordial tensor perturbations will be of the order of 10 power minus 23 or so. Evidently, these boosted scalar power leads to secondary gravitational waves of considerably high amplitudes. So let us now turn to non-Gaussianities. What are the constraints on non-Gaussianities on the CMB scales? The non-Gaussianities are characterized by these 3 non-Gaussianity parameters depending on the so-called shape of the bispectrum. I'm out of space and time to describe this. The bottom line is that FNL on the CMB scales, which is, you know, is consistent with 0. It's very small. And these constraints, as I have written, imply that slow-rolling single field models involving the canonical scalar field, which are favored by the data at the level of power spectra, are also consistent with the data at the level of non-Gaussianities. This is over the CMB scales. The question of interest is that when you have deviations from slow roll, they can lead to larger levels of non-Gaussianities. And what are the non-Gaussianities generated in the inflationary models we have considered? Well, these are plotted in these in these red curves here. This is in the so-called equilateral and the squeeze limit. And this is for an ultra slow roll inflationary model. This is for a punctuated inflationary models. You can ignore these spikes that arise. These spikes arise because the FNL is actually a ratio of the scalar bispectrum to the power spectrum. The power spectrum contains a spike, downward spike on these scales, and which leads to larger values of FNL. The bottom line is that on scales where the peak in the power spectrum lie of the order of 10 power 14 megaparsec or so, FNL we find is of order 1 or is of order 1. Therefore, it doesn't lead to significantly large FNL. Notice this is still about 10 power 2 times larger FNL than what is generated in slow roll inflation. What are the implications of this relatively larger values of FNL? Can it leave telltale signs on, say, omega GW? Well, FNL is usually introduced through this definition here. I'm sorry. FNL is usually introduced through this definition. This is the actual curvature perturbation spectrum. This is the Gaussian component, and FNL is introduced as the coefficient of the quadratic of this function of this Gaussian term. And using this relation here, you can calculate what is the corresponding 2-point function in Fourier space. It can be expressed as the conventional power spectrum plus a term that contains, this FNL, this term here. And we can treat this as the non-Gaussian corrections to my primordial spectrum. This is given by this expression, given an FNL of K, which we take into the, to be in the squeeze limit. I can clarify this if there are questions. We can calculate what is the correction to the primordial power spectrum, and that is what has been plotted in the ultra slow roll models on top and the punctuated inflationary models at the bottom. The red curve is the original power spectrum. The blue curve contains the corrections. Evidently, the corrections are small. These spikes again arise due to the spikes in FNL, and therefore they can be ignored. What it implies is that the corrections to omega GW are small. The corrections to FPBH also need to account for non-Gaussianities that can arise at the time of their formation, and this is something we are currently investigating. So I have probably a minute or two. I will just talk about how enhanced power can be generated from squeezed initial states. This is not difficult to understand. I'm sorry. This is not difficult to understand. If you're familiar with the modes describing the scalar perturbation, these are the de Sitter modes. What we have done is that we have introduced these quantities alpha k and beta k and written them as a superposition of these modes, and these alpha k and beta k are the Bogoliubov coefficients. Using these scalar modes, you can calculate the resulting power spectrum. Given a function of beta k, or in fact a ratio of beta k to alpha k, you can generate any feature you like in the primordial power spectrum. If you have a localized feature described by g of k, you can generate with this choice of alpha k and beta k. What is interesting about these squeezed initial states is that they lead to relatively large non-Gaussianities, particularly in the squeeze limit. What we have plotted here are the original scalar power spectrum in red here, and the non-Gaussian corrected power spectrum. Evidently, the corrections due to the non-Gaussianities are significantly large. We have plotted them for this so-called log normal distribution. And in principle, these large non-Gaussianities can lead to enhanced PBH formation and larger amounts of secondary gravitational waves, but there is an issue. What happens is as follows. You're working with non-vacuum initial states. It is well known that if you assume the inflationary perturbation to be in the vacuum state, the energy density in the curvature perturbation is much smaller than the background energy density, which is written as rho I here, which is 3h squared MPL squared, where hi here is the Hubble scale during inflation. But if you want to work with non-vacuum initial states, you need to ensure that the energy density of the curvature perturbation is much smaller than the background energy density. And if you ask, what does this condition lead to? I'm sorry, I went in the other direction. What does this condition lead to? It constrains this value of gamma here. And how much does it constrain? It constrains, very severely. What you find is that gamma is of the order of 10 power minus 15 or so. We have worked with gamma of less than 1 in plotting the curves in the previous slide, but we find that if you want to ensure that there is no back reaction, gamma is severely restricted, which essentially implies that you will have only slow roll power spectra and slow roll levels of non-Gaussianities, which are rather very small. So I have come to the end of my talk. Let me quickly summarize with a few remarks. So models of ultra slow roll and punctuated inflation can lead to enhanced power on small scales, leading to larger levels of PBH production and increased strengths of secondary gravitational waves, some of which hopefully may be detected in the coming future. Despite the significant levels of deviation from slow roll, we find that non-Gaussianities are not extraordinarily large. They are of order 1. And these non-Gaussianities, as far as omega GW is concerned, lead to insignificant corrections. And we have also examined whether squeeze states, initial states, can lead to such larger power and larger non-Gaussianities. Well, unfortunately, this issue of back reaction severely limits the deviations from the Bunch-Davies vacuum. With those remarks, I've come to the end of my talk. These are the 3 people with whom I had written these papers. Raghavendra, as I mentioned, is my graduate student working with me here at IIT Madras. Pankaj Saha is a postdoc working with me. And this is Professor Joseph Silk, who needs no introduction to the cosmology community. Thank you. Thank you very much for your attention.
Thank you, Sriram. So we have time for a couple of quick questions. So yeah, Suchetana, please unmute yourself and ask the question.
Hello, Sriram. Can you go to your summary slide, please?
Sure.
So,
yes.
so I was just trying to understand the motivation for these models of ultra slow roll or punctuated inflation, as you said, that it leads to enhanced power on small scales. So do you think that if you try to implement those inflationary models, like how much will it modify, let's say, the CMB power spectrum, and at which multiple values? And also, if I look at the matter power spectrum, so are there any, because my question, so the motivation I'm trying to understand, that why would we want that?
Okay, so we need to ensure that we are consistent with the CMB scales. Okay, so here I'm sorry, this is playing tricks with me. Here, so what do we wish to do? We want to enhance power here, but we need to ensure that over the CMB scales that we are consistent with the CMB data. That is, over these scales, NS is close to 0.96, and this tensor to scalar ratio, the blue is the tensor power, red is the scalar power. This ratio is less than 0.05 or 0.06. Okay, so all these models, there is a large level of fine-tuning involved to ensure that they are consistent with the CMB data. Notice the CMB data will end somewhere here, right? Somewhere here. All right, and we are working on much smaller scales. I hope that answers your question.
Yeah, so you are talking about much small k values, right?
Absolutely, absolutely. We are talking about 10 power 14 megaparsec inverse.
So
or
they
10 power minus 14 megaparsec.
So,
very small.
Let's see if there are other questions, Suchetana.
Yes. Okay. Yeah.
Kanhaiya, please unmute yourself and go ahead.
Hi, Professor Sriramkumar. First of all, thank you very much for this nice review talk. And also, I would like to advertise some of our recent works where we actually try to constrain the primordial power spectrum and also primordial black hole abundances using gravitational wave data. And I have one question. So,
I'm aware of your papers,
wave,
Kanhaiya.
Go
ahead with your question.
So, my question is that using the gravitational wave data, using the secondary gravitational waves, can we also constrain the scalar to tensor ratio? I mean, can we?
No, you can't.
Do that?
Okay. Now when I mean the scalar tensor ratio, as of now, I've been talking about only on the CMB scales. Okay. If you're asking, so on what scales are you asking? You are asking on the scales where there is a peak in the power spectrum?
The scales where.
Okay, so if you're talking about on the CMB scales, you need to ensure that they are consistent with the CMB data. I'm sorry.
So basically, yeah.
Can you repeat again? Kanhaiya, I'm not able to hear you clearly.
Yeah. So using the gravitational wave data which we have from LIGO, advanced LIGO and all, so the scales which that will probe, so can we probe the scalar to tensor ratio for those scales?
Well, the scalar to tensor ratio is this, right? On those scales, okay? Now, I don't know whether you mean the secondary, those are the secondary gravitational waves, right? That will be highly model dependent. Okay, so if you are talking about the tensor to scalar ratio, this primordial tensor to scalar ratio, notice it is the ratio of these two quantities. Okay, or this divided by this, which is very small. So I don't know whether you are talking about the look. Often what happens is that one talks about the primordial tensor to scalar ratio. Remember, this is the primordial gravitational waves. Okay, while those are secondary gravitational waves which are generated when the modes have entered the Hubble radiance. These are different from the primordial ones. Okay, the primordial amplitude of the primordial gravitational waves will be much smaller.
Yes. Yeah.
Okay, the omega GW associated with the primordial gravitational waves, let me try to go to that slide, will be considerably smaller. This is what I was trying to clarify. If you're talking about omega GW associated with the primordial one, it will be here, somewhere here, about 10 power minus 16. The second order primordial will be 10 power minus 23. These are second order secondary gravitational waves generated due to enhanced power after they've re-entered the Hubble radius. So I'm not able to completely understand your question, Kanaya. We can speak offline.
I guess, we can probably move on now, unless there are any pressing questions. I don't see any other hands. So thank you, Sriram. Thanks again.
Thank you, Tirth.
Yes. Yeah.
Remember, there is a Slack channel and you can always post your questions and comments there. There is a Slack channel dedicated to just this session.
Okay.
I will post the link once more in the chat box during the next talk. The next speaker is Shikhar. Shikhar, can you share your screen? Sriram, if you can stop sharing.
Yes, I'm sharing. I'm stopping sharing. Just give me a minute.
Okay, thank you. So,
yes.
Yeah, Shikhar, please go ahead, share your screen.
okay.
So Shikhar will be talking about Lyman-α coupling and heating at cosmic dawn. Shikhar, I will give you a warning at 10 minutes and please try to keep the talk to within 12 minutes. So we have few minutes for questions. Okay.
Okay. Okay, thank you. Okay, so I'll be just a minute. Okay, thank you. So I'll be talking about Lyman-α coupling and heating at cosmic dawn. So let us first go to the very basics of 21 centimeter signal. It is defined as the brightness temperature of 21 centimeter measured against the cosmic background. So when we solve the radiative transfer equation under the Rayleigh-Jeans limit, we can write the intensities in terms of temperature. And the simplified version of that equation is set up in this form. Over here, delta TB is the 21 centimeter signal which we measure. And in this equation, the YP, omegas, and H are the usual cosmological parameters. XHI is the neutral hydrogen fraction. Z is the redshift. T gamma is the CMB temperature, and TS is the spin temperature, which I'll define next. So the defining equation for the spin temperature is this. Here N1 and N0 are the population levels of the hyperfine levels. 3 is the degeneracy factor, and new 21 cm is the frequency corresponding to 21 cm line. So at cosmic dawn, it is mainly determined by two processes. One is the CMB photons, which affect the population levels through the usual Einstein 3 processes. And the other is the Lyman-α photon, which affect it through an effect known as the Wauthausen field effect. So when we make a balance of these two processes, we get an equation of this form. Over here, as I said earlier, T gamma is the CMB temperature and Tk is the gas temperature. And X alpha is the Lyman-α coupling, which determines the strength of this process related to the CMB process. So having set up the very basics of the 21 cm, I would just like to show an observation of this 21 centimeter signal made by the Aegis collaboration in 2018. So on the x-axis, I have the redshift. Time is in this direction, and on y-axis, I have the 21 centimeter signal on linear scale. So as you can see that there is this very deep absorption feature, which is the most intriguing part of this signal. It is thought that this first drop in the signal is probably because of Lyman-α coupling, and the rise of the signal is because of extra heating or reionization. So recently, based on this signal, Ghara and Melema have argued that a strong Lyman-α background is ruled out. So in this work, I would like to revisit their argument. So the first thing that we do in the modeling is to solve for the Lyman-α interaction and interaction with the hydrogen atom. So for that, we take the help of the radiative transfer equation. So the first thing that we do is make some approximations, because usually not all the complete equation is not necessary in generality. So when we make the diffusion approximation, we get an equation of this form. This is valid because the Lyman-α optical depth is quite high. So the diffusion approximation is valid, and we get the equation which is usually known as the Fokker-Planck equation. So the first term over here is indicative of the diffusion term. This is second order in the spectrum. The second term is the recoil term. Here eta is a recoil parameter, which basically is the ratio of momenta of the Lyman-α photons relative to the hydrogen atom. And finally, the third term is the expansion term. This captures the effect of the expanding universe. Here gamma s is known as the Sobolev parameter, which is proportional to the Hubble parameter. The right boundary conditions in this equation would be this. So as you can imagine, J alpha is the undisturbed background Lyman-α specific intensity, which far from the resonance should be which we denote here by J alpha. So when we make so here I'm showing a typical solution for the equation. Here on y-axis, I have the spectrum normalized by the background. So far from the resonance, you can see that it approaches 1 as it should. And this dashed line is the showing the undisturbed version. So the two interesting features of this absorption is, one is this asymmetry developed. This asymmetry is because of the expanding universe. So the Lyman-α photons uh, so the hydrogen atom in the lab frame would like to accept photons of higher frequencies, so that when it in its rest frame, it measures exactly at the Lyman-α frequency, because the sources are moving away in an expanding universe. And the other feature that is to be noted is the this shaded region. This is indicative of the Lyman-α heating that I will explain in a minute. So once we have obtained the Lyman-α spectrum, our first task is to write down the Lyman-α coupling. So intuitively, we can think that it should be proportional to the background. So, but with more rigorous calculations, the expression can be put in this form. Over here, J alpha is the background, and S is the distortion factor, which accounts for the shape that I showed in the previous slide. So it is usually of order 1. And J naught is some combination of fundamental constants and the CMB temperature. Okay, so next I would like to explain the Lyman-α heating and cooling mechanism at the microscopic level. So for simplicity, let us consider two extreme cases. One in which hydrogen atom is moving away from the source, and one in which it is moving towards the source. So if it is moving away, so like I said earlier, so it would like to accept photons of higher frequencies in lab frame, so that in its rest frame it is measured exactly at the Lyman-α. So these type of photons will speed up the hydrogen atom and hence cause an heating effect. And in the second picture, the opposite will be true. In over here, the photons of lower frequencies will be accepted, and these photons will slow down the atom and hence cause a cooling effect. So in a static universe, both these effects are equally likely, but in an expanding universe, we can think that this picture is slightly more dominant. And so we have a net heating effect. Okay, so once we have obtained the expression for the volumetric heating rate, we can insert it into an equation of this form. This is basically the governing equation of thermal evolution. I have written the time derivatives in redshift derivative, and over here the first term is the usual adiabatic cooling term, which exists because of the adiabatic expansion of the universe, and this is the the Lyman-α heating rate. Okay, so the final thing that the ingredient in the theory is to set up the model for the Lyman-α background. So we since at Cosmic Dawn, we have very limited information, so we make some simplifying assumptions. So the first thing that we assume that Lyman-α are directly produced from the stars, as stars, more and more stars are formed at Cosmic Dawn. So it tracks the star formation rate exactly. So for redshift of our interest, this is 30 to 14, which roughly corresponds to cosmic dawn. No real data exists. So we just extrapolate our theory for these redshifts. So we can estimate the star formation rate density by calculating the rate at which the baryons collapse in the dark matter halos by unit volume. And finally, we need the spectrum of the background. So basically, we need how many photons are emitted at what frequency. So that for that we assume the population 2 model from Barkana and Loeb 2005. And so so once all this theory is set, we would now like to see the results. But before that, I would like to this show two main questions that you would like to answer in this work. So one is, what is the correct expression of Lyman-α heating? And second, does the edges back collaboration rule out strong Lyman-α background? Okay, so now we'll see some results. So here I will show two panels. On the left, I have the evolution of the gas kinetic temperature, and on right hand side, I have the 21 centimeter signal. So on x-axis on both panels, I have the redshift from 14 to 30. The y-axis is in log scale for TK and linear scale for the delta TB. So the first result that I'm showing here is corresponds to simply an adiabatic cooling universe in which there is no radiation. So if there is no radiation, there is no coupling, and hence there is no signal observed. So that is why there is this flat line corresponding to 0. Also, just for comparison, this dotted line here is the CMB temperature, which is just 2.73 times 1 plus Z. And the TK would just be proportional to 1 plus Z whole square. Okay, so we next switch on the Lyman. Okay, thank you. Okay, so we now we switch on the Lyman-α radiation, and the green curve is the result, and this corresponds to a base model, which is the Barkana and Loeb's population 2 type stars. For exactly the same astrophysics and model parameters, I have shown the results from previous literature, Ghara and Mellema. So as you can see, there is a considerable difference between our results. So their result I have shown by dash dotted black, dash dotted line. This is the kinetic temperature, and this is the signal. So now the question is, why is there is so much difference between our results, even when we have the same model assumptions and parameters? So the answer lies in the volumetric heating rate. So actually, there are two types of expression for the volumetric heating rate by Lyman-α photons. They both are correct and equivalent. So their equivalence can be established through the some lengthy algebraic manipulations. So this is 1 and this is 2. And looking at these two expressions, I think it becomes quite clear that there has been some kind of a mix-up in the expression used by Ghara and Mellema, which is this third one. So we can, for completeness, we can also make a numerical estimate of their ratio of their heating rate with one of the correct ones, and we get a functional dependence of this form. A typical value of this function, this ratio comes out to be around 100. So moving on, we just want to show how does the signal and the temperature changes when we scale up our Lyman-α background. So as you can see, this is quite obvious. So if we increase the Lyman-α background, the temperature should increase. And if the temperature increases, the signal should shift to higher redshift. So the absorption feature will occur at an earlier time. For completeness, also showing the signal measured by the edges once again. So as you can see, there is a considerable difference between our theory and the experimental data. This is where the recent efforts have been diverted in theory, which there are two types of model, one which predicts excess cooling and one in which we have an excess radio. So we will not go into that detail. So I'll just now like to summarize my talk. In this work, we model a 21 centimeter signal with the Lyman-α heating. We have investigated various expressions of Lyman-α heating in literature. Our main conclusion is that Lyman-α background, a strong one, is not ruled out and is in fact necessary, although not sufficient, given the edges claim. But this is contrary to the conclusion of Ghara and Mellema. and we have discussed the reasons for this by identifying the shortcomings in the theory. Okay, thank you.
Thank you, Shikhar.
Okay.
So we have time for a few questions. So if there are any questions, please raise your hand. So, okay, since there are no hands, I have a quick one, Shikhar. The expression of Ghara and Melema, and I mean, the main difference, I guess, is the Lyman-α profile. Is it that phi alpha is the absorption profile?
This one?
Yes.
No, actually, so I think it's not just a profile. So I think it's has been some mix up. So this part has come from this one, and this has been this, so it's not completely right. So either this one or this one. So this is not derivable from first principles. So
I
both
see.
these.
So it's also the proportionality factors in front of the integral. Those are
Yeah,
also. I
correct,
see.
correct.
Okay.
So that, yeah.
And what happens there? Q alpha heating is large. So how do they then rule? I mean, how does it? I mean, if you go to the plot, plot, what happens there?
So okay, so like so the thing is that if for f alpha is equal to 1, so the Ghara and Melema result is this black dash dotted line, while my result is the green one. So because of the same parameters, so they agree that this strong Lyman alpha is not is ruled out, because if they go to say f alpha is equal to 100, the signal would just almost disappear. So for the same parameter, my signal is very low, which is comparable to, at least somewhat comparable to edges, while there is actually very off.
I mean, basically they're heating so efficiently that the signal just gets vanishes.
Yeah,
okay.
Exactly.
I understand. Yeah. Are there any other questions? Okay, if not, let's thank Shikhar again, and we can move on to the next talk. That is by Aritra Kundu. So Aritra, can you start sharing your screen?
Yeah, just 1 minute.
Yeah.
Is it visible?
Yes. Would you like to make it presentation mode?
Okay, is it fine now?
Yeah, this is fine. So our next speaker is Aritra Kundu, and he will be talking about cosmic recombination history in the light of recent edges measurements. Aritra, please go ahead. I will give you a warning at 10 minutes, and you should try to wrap up within 12 minutes. Okay. Yeah,
so good evening, everyone. I'm Aritra Kundu, a master's student at Presidency University, Kolkata. Today, I will be talking about cosmic recombination history in the light of the edges signal. This work has been done in collaboration with my supervisor, Dr. Kanan Datto, and my colleagues Ankit Pal and Ankita Bera. Now, we are all familiar with this type of picture and have seen it in almost every early universe cosmology talk. This basically shows the evolution of the universe from starting from Big Bang to its present age. That there are three important eras after the universe became neutral after recombination. The first is the cosmic dark ages, which is devoid of any light producing sources. Then we have cosmic dawn, where the first stars and galaxies started to form. And finally, we have reionization, where the universe was again ionized due to the radiation from these first stars and galaxies. Now, as the previous speaker mentioned, that one of the most important tools to study these eras is the 21 centimeter line of neutral hydrogen. It basically arises due to the spin flip of the electron in the ground state of neutral hydrogen atom. As the name suggests, it has a reference wavelength of 21 centimeter, but due to the expansion of the universe, we see a redshifted version of this wavelength. The number density ratio between the triplet and the singlet states is given by this formula, where G1 and G0 are the respective degeneracies of the states, and so this ratio is 3. T star is simply h nu by kb, which has a value of 0.068 Kelvin. And the important quantity to note here is Ts, which we define as the spin temperature. It basically tells us what would be the number density ratio if the temperature is at Ts. Now, the spin temperature is of utmost importance in 21 centimeter cosmology because it depends on other physical temperatures like the CMB temperature and the gas temperature via various coupling processes. The values of the coupling coefficients and also the temperature determines how strongly will the spin temperature get coupled to a particular temperature. When the CMB photons pass through the intergalactic medium, the photons interact with the neutral hydrogen in the cloud, and what we see is actually a difference between the spin temperature and the CMB temperature. This is defined as a differential brightness temperature, and not only depends on the redshift but also on the position. So we take an all-sky average, which gives us the global 21 centimeter signal. The important quantity to note is the last term, because this term determines whether the signal would be in emission or absorption and what would be its amplitude. If we plot the global 21 centimeter signal against redshift, we can easily see the three important errors imprinted in it. The first is the cosmic dark ages, which has an absorption signal due to a high value of Xc. Because of this, the spin temperature gets coupled to a low gas temperature, and so we see the signal in absorption. We also see another absorption signal in cosmic dawn, but this is due to the high value of X alpha, that is the flux coupling coefficient due to Lyman-α photons. There here also the spin temperature gets coupled to a lower gas temperature, and that's why we see the signal in absorption. Finally, due to the heating from the first stars and galaxies, the intergalactic medium temperature rises, and so we see the signal in emission. Now, for our work, the absorption signal from cosmic dawn is important because it was claimed to have been detected by AGES in 2018. When the AGES team reported their results, it created a lot of buzz in the community because the amplitude of the signal was 500 millikelvin, and it was much larger than what was predicted by standard cosmology. But there are some issues regarding the analysis done by the AGES team, and so we need confirmation by other independent experiments to say anything conclusively. Nevertheless, if we consider the signal to be true and indeed assume that it has such large amplitude, then we cannot explain it via any standard astrophysical process. To explain the amplitude, we either need a colder gas temperature or an excess radiation, because the amplitude depends on the ratio between the radiation temperature and the spin temperature. We explored the colder intergalactic medium scenario and tried to study its impact. As I said, that we do not know any known astrophysical process that can predict the colder intergalactic medium. But for the baryons to have a low temperature, it must interact with something that is colder than itself. And there is one thing that is colder than the baryons, that is dark matter. Normally, baryons and dark matter do not interact with each other. But if we consider some interaction, then we can see that it will lead to a colder intergalactic medium, which leads to a deeper absorption signal. And not only that, it enhances the hydrogen recombination rate that suppresses the ionization fraction. To see the evolution of the IgM temperature and the recombination history, we need to solve these equations. I thought it would be better if I explain the physical processes involved through a schematic diagram. So at first we consider no DMB interaction, that is the standard scenario. Here the baryons and dark matter are both affected by the expansion of the universe, which leads to adiabatic cooling. Since baryons interact with photons, they can get heated up with the radiation from the CMB or the first stars or quasars. The ionization fraction of hydrogen is coupled to the IgM temperature or the baryon temperature. So any change in the IgM temperature will get reflected on the ionization fraction. At lower redshifts, the extra photons from the first sources ionize the neutral hydrogen, thereby leading to reionization. Now, when we consider DMB interaction, there will be heat exchange between the baryons and dark matter due to the temperature difference. Also, since there is a relative velocity between the baryons and dark matter, it will lead to heating because of the frictional term. Now, if we see the evolution of the gas temperature by taking into account of the DMB interaction and compare it with the standard scenario, we can see that it leads to a colder intergalactic medium. Now, in this plot, we have considered two sets of parameters of dark matter mass and interaction cross section. Sigma 45 is basically the interaction cross section divided by 10 to the power minus 45 meters square. And we can see that for a low interaction cross section value, the evolution kind of remains same as in the standard case, but during the cosmic dawn, we do see a lowering of the gas temperature. But for a high interaction cross section, the baryonic temperature decouples earlier from the CMB temperature and remains coupled to the dark matter temperature. Thereby, we get a much lower temperature of the IgM, and which will lead to a much larger amplitude. At lower redshifts, X-ray heating starts to dominate, which heats up the IGM, and and ultimately it leads to reionization. But the main motivation for considering DMB interaction was the amplitude of the edge signal. So we wanted to see that how the amplitude of the edge how we can model the amplitude by considering the DMB interaction and also X-ray heating. In this plot, we have considered three sets of star formation efficiency values and compared them with the edge signal. For a high star formation efficiency, we can see that the heating starts from an early redshift, and so the amplitude is not too deep. But for a low star formation efficiency value, the heating begins at a lower redshift, and so the amplitude of the signal is quite high. But for a f star equals to 0.01, the amplitude sort of is similar to the edge signal. For all these plots, we have considered this set of parameters of dark matter mass and interaction cross section. Now we wanted to see that whether how the colder intergalactic medium changes the recombination history of the universe. So on the left hand side plot, we evolved the ionization fraction and for two different star formation efficiency values, and we saw that for due to colder intergalactic medium, the ionization fraction gets suppressed. It might not be evident from the upper panel, but if we look at the percentage change in X in the lower panel, we can see that for F star equals to 0.01, the change in the ionization fraction can even rise to about 30%. On the right-hand side plot, we considered a last set of parameters of dark matter mass and interaction cross-section, and plotted their percentage change in X on the y-axis and the respective brightness temperature on the x-axis at redshift 17.2. Now we can see that for that the change in X can be anything from 0 to 40%. But even if we measure the signal at this redshift more accurately, then also a large uncertainty remains in the percentage change in X. So there is a lot of degeneracy in the dark matter baryonic interaction models. They will predict, though they will predict the same brightness temperature, but the change in the ionization history at this redshift will be different. We thought that whether we could then use the edge signal and this change in the ionization fraction to constrain the DMB interaction. On the left hand side plot, we can see we show a constraint plot that we can see that for low mass dark matter mass and high interaction cross section, the suppression of the ionization fraction is more. As I said that to put stringent constraint on the DMB interaction models, we need to we cannot do that if we consider the measurements at single redshift. So we took the edge signal at another redshift, that is 15.2, and tried to see the overlap of both the regions in the parameter space. We can see on the right hand side plot that if we consider two different redshifts, then we can rule out a large region of the parameter space and thereby reduce the uncertainty or the degeneracy in the DMB interaction models. So to put further constraints, we need to know the entire recombination history of the hydrogen, recombination history of hydrogen.
Aritra, you have 2 minutes.
Yeah, let's conclude. So to conclude, I like to summarize my talk with the following points: that ages measurements needs confirmation by other independent experiments. But if it is confirmed and if it is found to have such large amplitude, then it either needs a colder intergalactic medium or a strong radio background. To have a colder intergalactic medium, DMB interaction can be a viable option, and we saw that it enhances the hydrogen recombination rate, thereby leading to suppression in the ionization fraction. We also saw that there is a lot of uncertainty in the change in ionization fraction if we consider the edge signal at a single redshift. So the knowledge of the entire recombination history or measurements at multiple redshifts will be required if we want to reduce the uncertainty and rule out a large part of the DMB interaction models. Lastly, I'd like to say that we need to consider other physical processes like the Lyman-α coupling, because in this case we have only considered the X-ray heating. So we need to consider Lyman-α coupling, dark matter annihilation, and also the effects of primordial magnetic fields to have a complete picture. Finally, I'd like to end by saying that the 21 centimeter signal will not only help us to understand the physics at the of the early universe, physics of the early structures, but it will also open up a new avenue for astroparticle physicists to study the properties of dark matter. Thank you.
Thank you, Aritra. We have time for questions. So if somebody wants to ask a question, please raise your hand in Zoom. Shantanu, please unmute yourself and ask the question.
Yes, so with the edge signal, can you constrain dark matter interactions or self-interacting dark matter?
No, we haven't considered the self-interacting dark matter models here. We just considered the DMB interaction because it was found that if we consider DMB interaction, then we can sort of explain the amplitude of the edge signal. So we haven't considered the self-interacting dark matter models.
Okay. Are there any other questions? Arnab, please unmute and ask the question.
Hi. So, is your model can explain the width of this Gaussian profile of edge signal?
No, we till now we have just been able to explain the amplitude, but to explain the width of the edge signal, we need to consider other physical models. First of all, we really need to consider Lyman-α coupling, and we need to also see that whether dark matter annihilation or primordial magnetic fields can explain the width of the signal or the shape of the signal.
Okay, thanks.
Thank you. Yeah, Kanaya, please unmute and ask the question. Kanaya?
So what's the nature of the, am I audible?
Yes, yes.
So my question was that what is the nature of dark matter baryon interaction?
So in most of the papers which have considered the interaction, DMB interaction to explain the edge's amplitude, they have.
So what's the nature of it? Like, so the interactions are through
the interaction is not purely Coulomb, but some kind of Coulomb-like, and the interaction model is velocity dependent, and this model helps us to sort of evade the constraints from other experiments like CMB, because this, if we consider this model, then we can only explain the amplitude during the cosmic dawn by not violating the other constraints. And so the interaction which they have considered, these models consider, is like is Coulomb-like, but not exactly Coulomb. And in some papers, they have also considered small charge of dark matter particles, but they is just a small component of the whole dark matter models.
Okay, let's thank Aritra again, and it's time to move on to the next talk. So our next speaker is Arnab. Arnab, if you can start sharing the screen. So Arnab will be talking about the first multi-redshift limits on post-EoR 21 centimeter using uGMRT. Arnab, please go ahead. I will give you a warning at 10 minutes, and please try to wrap up within 12 minutes.
Okay, fine. Hi everyone, I am Arnab. I am PhD student at IIT Indore. I will be talking about the fast multi-redshift limit we get on post-EoR H1 power spectrum at redshift 1.96 to 3.58 using an upgraded GMRT. So this is the observational effort, and there are other members across India of this observational project with uGMRT. And so let me tell you very briefly that we know the universe is almost completely ionized by redshift 6. However, we are interested in the post-Epoch of reionization era, where the H1 is contained in very dense self-shielded region, and we are not interested in detecting emission from individual sources, whereas we are interested in the H1 intensity mapping, where the H1 is a kind of a diffuse background, collective emission from all these sources, and we want to estimate the fluctuation in this diffuse background to quantify the H1 power spectrum in this post-EoR era. So what we have done, we have taken data of LS North 1 field, which is high in galactic latitude, so that we expect the uh, effect of foreground emission is less, right? And effect of galactic synchronous emission is less, and also it is up in the night time, so the effect of RFI and also the ionospheric perturbation will be less. So we have observed this in the band 300 to 500 megahertz using uGMRT. So this is the map of the LS North 1 field at 400 megahertz. We have only performed the direction independent calibration pipeline developed by us, and we reach an RMS 15 microjoules per beam, and the and this circle is the pioneering card of the GMRT at 400 megahertz. And we have 3,500 clean components which we have subtracted from our data set, and we take the residual data to estimate the H1 power spectrum. So here we have incorporated the foreground avoidance technique, so basically the foregrounds will be dominated in the low k parallel modes, whereas it will when it is coupled with the instrument response, chromatic instrument response, it is kind of appear in a wedge shape region, which we call popularly foreground wedge, and one can search for H1 signal outside this horizon line, which is popularly known as uOR window. So this foreground avoidance technique has already been applied to MWA and HERA dataset, and this is we have tried to apply here with our uGMRT observation. So basically what we measure the visibility, and which is a Fourier conjugate of the sky emission, sky signal, and then one has to transform this visibility from frequency to the delay domain by a simple Fourier transform along the frequency axis. And then when we have this delay domain visibility, we can just cross multiply it or square it to get the power spectrum after proper scaling, multiply it by the proper scaling factor. And then one can do the estimate the cylindrically average power spectrum, 2D power spectrum, and then average the modes in spherical domain or spherically averaged three-dimensional power spectrum. So this is basic definition of our power spectrum estimation pipeline. However, there are some caveats. One is that there are the RFI flagging. The problem is that in the right panel, I am showing you here a single baseline in the time frequency domain, and this yellow patches are the flagged region, right? And if I do the Fourier transform along this frequency axis, this non-uniformly sampled data will create oscillation in the delay domain. So as a result, which is the k parallel axis is your proportional to the Fourier conjugate of this frequency axis, what will happen that foreground will leak from the wedge into your uOR window. So your uOR window will be corrupted. So one can think of this in the Fourier convolution theorem, this problem where the visibility in the Fourier domain, that is in the delay domain, is convolved with a sampling function, which is S nu. S nu basically gives you 1 and 0, right? 1 is for non-flagged channels and 0 is for flagged channel. And W nu is a spectral taper function, which can deal the sharp edge at your band shape. So what we want to deconvolve this term from our delay spectra, so that we can get this visibility in the delay domain. So let us give me at a simple example where we have flagged a single visibility spectra in frequency domain, 15 channels, that is let's say 15% data is being flagged. And if we do the Fourier transform, what we can find that beyond this horizon line, this vertical line, there is a huge spillover of foreground from the foreground wedge to the uOR window. However, if we apply the one-dimensional clean algorithm, then we can actually reduce this foreground spillover, and we can go to the signal level. So we have applied this one-dimensional clean algorithm in the delay domain to deal with the RFI flagging samples. Next, our visibility also contains the H1 signal, foreground and noise. So if we just do the square of this visibility, there will be a huge positive noise bias. So what we have done is that we incorporated the idea proposed by Bharadwaj and Sethi almost 20 years back, that we divided our visibility domain, this is U and V, in the visibility domain into small subcells, and these are the data points, right? And these cells are basically inversely proportional to your primary beam. Now, whatever the visibility points falls in this cell, we cross correlate these visibility points among each other. So we get a correlation matrix for each cell, and whose diagonal elements are the self correlation which contains the noise bias. However, the off diagonal elements are the correlation among the visibilities with each other, and we assume that the noise is not correlated between two visibilities. So what we get, if we take the average of this off diagonal term of the correlation matrix, that will be free of noise bias, and we quote it as the power spectrum for that particular cell, right? So this is the two-dimensional power spectrum estimated by our clean PS pipeline at redshift 3.58. As we can see that foregrounds are contained within a wedge-shaped region here, and this black line is a horizontal line. So we choose these modes which is bounded by this white dashed curve to estimate the spherically average three-dimensional power spectrum. So we quote the uncertainty in the power spectrum as the noise power spectrum divided by number of modes averaged coherently. So in the right hand side, you see this is the simulated result shown in Liu et al. Adrian Liu 2014, that the uncertainty in the power spectrum also show a which kind of region where the covariance due to foregrounds are dominated in the foreground wedge, whereas the thermal noise covariance is dominated in the uR window. So we found this from the data set of our uGMRT data set, and we found the similar kind of nature here also, and we take these modes to code the uncertainty in our power spectrum, right? And this is the spherically average power spectrum at 3.58. This black line is our estimated power spectrum. The blue dash line is the theoretical estimate of the thermal noise power spectrum. As we can see that we are not very far away from the theoretical estimate, and this is gives us the upper limit. However, this lower green line is the theoretical expectation of the H1 power spectrum at this redshift, and the dark matter power spectrum is shown in the magenta. So we can see that we are still 3 to 4 orders of magnitude higher than the expected signal, and this gives us the stringent upper limit at redshift 3.58. Next, we check that upon integrating, so data has been taken over the 4 nines. So if we integrate the data in the visibility domain over different nines, we should expect a systematic decrease, and we found the same thing here also. Upon integrating more nines of data set, we see that there is a systematic trend in decreasing of the power spectrum. So we think that our estimation pipeline works well and give us a consistent result. Then we have done our jackknife test where we divided our 8 megahertz chunk of the bandwidth around 3.58 into two 4 megahertz part, and we estimate the power spectrum, and we found that this is also consistent with the expected value. Then we choose for 3 other 8 megahertz chunks which are less dominated by RFI at redshift 1.96, 2.19, and 2.62. The upper panel gives you the two-dimensional cylindrical average power spectrum, and the lower panel is the spherically average power spectrum, where we average the modes inside this white dashed line, spherically average these modes, and estimate the three-dimensional power spectrum. And we found that we are for all cases we are close to the theoretical thermal limit, and this gives us the best upper limit at this redshift on the post-EoR H1 signal. So here I have plotted the power spectrum as a function of G, where we have taken the value of the power spectrum, that is the upper limit of the power spectrum at k equals to 1 MPC inverse, and here we show the how the evolution of this upper limit as a function of redshift. And on here also I plotted the H1 power spectrum, the redshift evolution of H1 power spectrum, and the dark matter power spectrum. Dark matter power spectrum is being calculated from CAM code. So given the 13 hours on source data before fragging, we put the upper limit at these redshifts, and we see that still we are almost 3 orders of magnitude higher than the theoretical expectation. So lastly, what we try to find out that we know the H1 power spectrum at post-EoR is a biased tracer of the dark matter power spectrum, right? So dark matter power spectrum has been calculated from CAM. We have the value of H1 power spectrum. If we put the value of spin temperature, we can constrain the parameters omega multiplication product of omega H1 and BH1, and we find out that this is these are the upper limits on omega H1 and BH1 at redshift Z equals to 1.96 to 3.58. However, the bias is close to 1 at this redshift region. So we found that this is still two orders of magnitude higher than the theoretical expectation. This is the theoretical expected value and theoretical and also observational constraint on omega H1 parameter as a function of redshift from DLS and other surveys. And we found that we are still 2 orders of magnitude higher.
So Arnab, you have 1 minute.
Yeah, so we think that we have not performed any subtraction or any kind of weighting, so fancy weighting of covariance matrix of our data set. So we don't think that we are we are not losing any signal, and we have not tried to model the diffuse foreground here also. We just go for foreground avoidance. So we think that we are not seeing here any signal loss. And lastly, what there are still some challenges which needs to be addressed in future. That is, we have to incorporate the direction dependent ionospheric calibration. We have to find out what is the residual gain correlation of the residual gain error in our power spectrum estimation pipeline, polarization leakage, variation of beams, etc. So lastly, I will point out that our original goal was to detect or was to put limits on EoR band with uGMRT. We already have the data at 120 to 250 megahertz. However, the challenge is that the RFI scenario is extremely bad. I have tried to analyze that data set, but the RFI is extremely bad, and also the beam information at 150 megahertz of uGMRT is still not available. That is, band 2 is still empty, and in future we hope to analyze that data set and put limits on the EoR window using uGMRT. Thanks. I will stop here.
Thank you. So we have time for questions. So if anybody wants to ask a question, please raise your hand in Zoom. Shantanu, please unmute yourself and ask the question.
It's a more general question, not maybe directly related to your team, since I'm just curious, as I don't work in this particular field. So I guess, can uGMRT confirm the edges signal?
Yes, there is a paper by Somnath Bharadwaj and Suman Chatterjee at NCRA, and Somnath Bharadwaj from Kharagpur IIT, that due to the edges signal, there is a huge amplitude, right, in the global spectrum. So in the power spectrum domain, it will give you a large amplitude in the power spectrum. So they showed that with say 1,000 hours or so, no, 100 hours of observation using uGMRT, we can still detect the power spectrum from this band. However, that that correlator is still not operational at I think 70 to 80 megahertz band at uGMRT. So in future, maybe this can be done. Right.
Thank you.
Okay. Are there any other questions? Okay, if not, I think we can move on to our next speaker, which is also the last talk of the session. So Kamal, can you start sharing your screen?
Okay, yeah, sure.
So yeah, we have one speaker who has dropped out in between. So Kamal, it's your talk now. So yeah. So Kamal Bora will be talking to us about constraints on the variation of alpha from joint SPT and XMM-Newton observations. Kamal, so I will give you a warning at 10 minutes. Please try to wrap up within 12 minutes or so. So we have time for questions. Yeah, you can start.
Okay, yeah, sure. Okay, so good evening, everyone. Myself, Kamal Bora. Am I audible?
Yes. Please go ahead.
Thank you. Myself, Kamal Bora, and I am from IIT Hyderabad. So today I will talk about one of the most fundamental physical constant, that is fine structure constant, and whether it is actually a constant or whether it is varying with time or space. So let's start. So I will start with Saunier-Joule-Davis effect, which is the spectral distortion in the CMB spectrum due to inverse Compton scattering between the CMB photon and the hot gas electron. So this is the pictorial diagram for the SZ effect. So this effect is characterized by the by a parameter called Compton parameter, which is given by this equation, and which basically tells us about the integrated pressure along the line of sight, and then this is a slide dedicated to the South Pole Telescope, which is a 10-meter aperture telescope located at South Pole, and which operates at frequency bands 95, 150, and 220 gigahertz, and the angular resolution of 1 arcminute. So the main goal of this South Pole Telescope is to perform a large survey for galaxy cluster detected by the SZ effect, and to study the CMB radiation. Now, this SZ effect has a one special quality. This SZ effect is redshift independent. Hence, it can detect the cluster up to the much higher redshift. This can be seen here. So this black and green dot from the SZ survey. This black one is from SPT-SZ survey, and green one is from ACT survey. So this SZ survey can detect this cluster up to the higher redshift. Now, we use 58 SPT cluster data from Bulbul et al., which spanning the redshift range 0.2 to 1.5, and detected by the SPT telescope along with the X-ray measurement from the XMM-Newton telescope. Now, basically, we have used these two parameters, which is called YSG and YX, in this whole paper, which basically are the different proxies for the thermal energy of the cluster with different scaling with alpha. So in the next slide, we will see how this YSG and YX depends on the alpha. So let's start with YSG. So the Compton parameter, which is defined by this equation, which I have shown earlier, and this equation, this Thomson cross section, which is sigma t, is given by this equation, which is a function of alpha square. Okay, now this integrated Compton parameter, which is given by this, if you integrate it over a solid angle over the cluster, then if you combine these two equations, you will get something like this. Okay, this YSG TA square, which is proportional to sigma t. And if you assume this ICM gas and ideal gas, then you will get something like this. So this dA is the angular diameter distance to the cluster. And now if we model the variation of alpha as like this, this alpha naught is the current value of alpha, and phi z is the redshift dependent part of the alpha. So we can write the fractional variation in alpha like this, phi z minus 1. Now, if we combine 3 and 4, these two, we will get this dependency YSG dA square, which is directly proportional to phi z square. Okay. Now, in the original SPT paper, they have calculated this YSG in this cylindrical volume within a radius of 0.75 arc minute. So what we have done that we have converted this cylindrical to spherical volume within R500, where R500 is the radius within which the mean mass density is 500 times the critical density of the universe. And this PR is the pressure profile of the ICM gas, and which we have taken the universal pressure profile. So now, moving to the X-ray part. So this YX, which is the proxy of the thermal energy of the cluster, is parameterized by this equation, where mg is the mass of the gas within radius r, and Tx is the X-ray temperature of the gas. Now this gas mass scales with alpha as minus 3 to the power 2, along with dl and dA, where dl is the luminosity distance to the cluster, and dA is the same angular diameter distance to the cluster. Now these two distances are interlinked by this relation called CDDR relation, which is given by this equation, dl equal to 1 plus z square dA. Now the variation of alpha is intertwined with CDDR relation. So when we are searching for variation in alpha, so we have to modify this general CDDR relation. So this modified CDDR relation is given by this equation, where eta z is a parameter. So now if we combine 1, 2, and 4, so we will get something like this. This Yx, which is proportional to phi z to the power minus 3 by 2 and eta z. Now this phi z and eta z are related by this equation. So basically this eta z depends on the variation of the fine structure constant. So if you substitute this phi z over here, this eta z over here, then we will get this yx, which is depends on inversely depends on phi z. So now if we take the ratio of this yz dA square and the yx parameter, then we will get something like this ratio, okay, where cx is a constant. And now if we parameterize the variation in alpha by this runaway dilaton model, which is given by this equation by after appropriate approximation, then this is phi z equal to 1 minus gamma log 1 plus z. So gamma here quantifies the hadronic coupling with scalar field with dilaton field. So if we substitute this phi z over here, then we will get something like this. So from numerical simulation and observations, we expected this ratio to be a constant with a scatter of 5 to 15%. Now this is the plot between yz to yx ratio versus z, and we can see that this ratio is nearly a constant as a function of z. So we can safely say that that we found no significant temporal variation in the yz-yx ratio for SPT data. Now, if we move to the spatial variation, then this is the model which we use for spatial variation from Gully et al. And the R is the look back time here, which again depends on the cosmological model, and we have used the flat lambda CDM cosmology here, and cos theta is the angular position between the cluster, between each cluster and the best fit dipole position, which is given by this RADEC coordinates, and which we have taken from Webb et al. Now, if we do a little bit math, then we will get the ratio. Then we will get something like this. So where this a equal to y0 to the power 1 by 3 and b equal to a y0 to the power 1 by 3, where y0 is the value of this ratio at a particular redshift. Now, now this plot shows the yz to yx ratio as a function of r cos theta, which again we can see that is nearly constant as a function of r cos theta. So here we can say that that we found no significant spatial variation in this ratio for the SPT data. Now, to confirm our analysis, we maximize the log likelihood function, which is given by this expression, where sigma is the total error in the ratio. So we also added our term, this intrinsic scatter term, as a free parameter here. So now now by using MCMC sampler, we get something like this. So these diagonal plots shows the 1D likelihood distribution for different parameter. This is for gamma, this is for C, this is for intrinsic scatter, and these are 2D joint contours for these parameters. So the value of gamma suggests that no temporal variation, and the value of C, which is close to 1, gives the idea about the isothermality of the cluster. Now we did the same analysis. We repeat our analysis. Okay. So we repeat the same analysis, same log likelihood this function for spatial variation, and we got the plot something like this. And this value of A shows the no spatial variation in finite state constant. And now this first table shows the comparison our result with previous studies, and the all studies here are from cluster data, and the second table shows the result this for spatial variation. So for spatial variation, we repeat our analysis once again for by taking without CDR violation, and we found no significant difference between them. And however, we can see that this bound from the quasar data is much robust than this what we found from cluster data. Now we conclude that we found no significant temporal variation in fine structure constant and no special variation in fine structure constant. Okay, thank you so much. Yeah, I'm done.
Yeah, thank you, Kamal, for the talk. So we have time for questions. So if anybody wants to ask a question, please raise your hand. Suchetana, please unmute yourself and ask the question.
Hello, Kamal. So what do you mean by spatial variation?
Okay.
Constant?
I mean position dependence.
Position dependence of what? So you mean the position of the cluster, or
how? Yeah, position on the sky.
Yeah,
Can you show the equation? I think that is answered. I think you have to go to this. Yeah, this one.
But is there any expectation that there will be position dependence? I mean, with time, people have been looking at that the temporal variation. But is there any reason for it to be dependent on position?
Yes, actually, there is a claim by Webb et al. They found that from CAG data, they found that this alpha is varying, alpha is decreasing with high rate at high redshift. But the same group found this Webb et al. From VLT data found that this alpha is increasing with at high redshift. So that's why there is a this discrepancy between these results.
Yeah, so they also found a dipole variation. I think recent results, I think I failed to confirm it, but I think this Webb et al., which is 2011, have found a dipole variation. It is slightly controversial, but they have found it. So.
Okay, thank you.
Okay.
Okay, any other questions? Okay, if not, then I think we can thank all the speakers again. I will clap on behalf of everyone. And yeah, and I would just like to again tell everyone that there is a Slack channel, and I think people have already started posting there. So I request all of you to carry on the discussions there if you want to. And before we end, I just wanted to check with the organizers if they have any announcements to make.
Nothing from my side, Tirth.
Yeah. Okay, then that brings us to the end of the session. So thank you all again for attending it. And have a nice rest of the SI meeting. Ajit, I think we can stop recording.